Hello, this is Qiongxiu. Welcome to my presentation titled as Privacy Preserving Distributed List Squares via Subspace Perturbation. This is a joint work with Richard Heusdens and Mads Christensen. I will follow this agenda to introduce this paper, and now let's start with the motivation. So the first thing is why do we focus on distributed system? So compared to a centralized system that is totally dependent on the centralized authority to take care of all the data collection and computation, which is very vulnerable to malicious attack. If the centralized authority is being hacked, then the whole system is broken. So this is why we have distributed system where we allow each participant to contribute equally in the whole system, and even though one or two parties were dropped, the whole system can still function properly. Another thing I would like to motivate is the privacy issue in smart meters. Here is the daily power consumption data of a household. It doesn't look very sensitive information, right? It's just your power consumption data, not your fingerprint, not your facial images, not your bank account number. But actually from this simple power consumption data, a lot of information can be inferred. For example, how many people are living in your house, and even your health condition, like whether you are disabled or not. So from here, we should really see that there's no real separation between your data and your identity. We should be very careful whenever we are asked to share our data. Now let's go to the problem setup. We first model a network as a graph with a number of nodes and a number of edges, and we can see here is an example with 5 nodes and 6 edges. And over the network, we would like to collaborate on minimizing the sum of all the local objective function. And here, the local objective function is given by this quadratic term. And here, yi is the decision factor at the node I, and qi is the features, is the observation or features at the node I. So, and overall, we also need to follow certain constraints. For example, here we would like each node I in the network have the identical solution. So we would like xi and xj to be exactly the same. And we conclude that there are two main requirements we should satisfy. The first thing is, of course, we would like to get our optimum solution. Here is given by this expression here, and we can see that the Q is we stack the big Q matrix is we stack all the local Qi together a big Q matrix, and the same also holds for I. We stack all the Yi together, and then we get this Y vector. And in the meantime, we would like to protect our individual privacy, which is our own observation, our own local information, Yi and Qi, to be protected from revealing to others. There are many ways to solve this problem, and here we give an example using PDMM. PDMM is an alternative of ADMM, but it is characterized with a faster convergence rate. This extended augmented Lagrangian function of PDMM is given by here. Now let me introduce you the notation here. C is the constant for controlling the convergence rate, and here lambda is the dual variable, and each edge here we have 2 dual variables. So this is why the dimension of lambda is twice the number of edges. And here C and PC matrix is corresponding to the instance matrix B of the graph. And overall, we need to have this updating function to update this X and lambda. And now let's see why, by inspecting the local updating function of PDMM, let's see why does the conventional approaches violate privacy. And one thing we can see here is that the PDMM is a broadcasting protocol. So whenever we need to update the lambda ij, the node j need to update this lambda ij. We can see that this lambda ji and the xj is already available at the node j, and then after receiving the xi from node I, then the node j can update its own dual variable itself. So that this is why it is a broadcasting protocol, which is very efficient in terms of communication. And from here, we can see that the local objective function. And when we want to update this xi, we need to find out its gradient, right? And this gradient, it contains information regarding your private data, qi and yi. So this is why when we share this xi, there's a potential that we reveal information regarding this local objective function if ixi. So this is why the privacy is violated. Now let's see how the state of art deal with this problem. The first one is the secure sharing approach. It tries to, for example, for each sensitive information, it tries to split each sensitive information into several pieces and then to distribute it or along the network. This kind of approach is very communication demanding, right? And the second approach is differential privacy. It tries to first add noise on top of your sensitive data, and then to send out the obfuscated data. In that case, your private data can be protected, but there's a trade-off between privacy and accuracy. Now let's go to the proposed approach. One fundamental thing I would like to introduce is that using noise insertion to achieve privacy preservation. Let's say the private data is X and the noise is R, and here both we can have the additive term and the product term. We can see that using the both cases, as long as we increase the noise variance, here the x-axis, we increase the noise variance, then we can see that the mutual information will be decreased. The mutual information mirror how independent is these two random variables. So we can see that as long as we increase the amount of noise inserted, then we can have less privacy leakage, right? Now let's go to the proposed approach. So by inspecting the X updating function, we can see that we have this gradient term and we have the summation of the dual variable. So the motivation comes from the fact that since we have this additional dual variable term, instead of inserting another noise term that is irrelevant to this updating function, why not just exploit what we have now here, the lambda as the dual variable as the noise? So let's see how would the dual variable converge. Because its convergent behavior will determine whether it is useful or not. So let's consider two successive lambda update, and we can see that let H denote the span of C and the span of PC matrix, and then we can see that every two successive lambda update will only happen in this subspace H. So this is why we can always decouple this lambda into the projection into the subspace and its orthogonal projection, and it is proof that this projection will always converge to a fixed point, and then this part will not change but only be permuted at every iteration. And we propose to exploit this one since it's only dependent on the initialization of lambda 0, right? So we can exploit this one, and we can make its noise variance to be very big, such that it can protect our private data. And one good thing of this property is that this non-converging property of dual variable will not affect the accuracy of X, because from the objective function we can see that from here we can see that this non-convergent part is orthogonal to this X, and then we can see that it does not affect the accuracy of the solution. So there's no trade-off between privacy and accuracy. Since we are relying on the subspace noise, it is very important to make sure that the subspace is always non-empty. And indeed, since the subspace is constructed by this C and PC matrix, and we can actually interpret this C and PC matrix as a new instance matrix of a new bipartite graph with twice the number of nodes and twice the number of edges. And we all know that the instance matrix of a graph is always rank deficient. So this is why as long as this m, the number of edges is not smaller than the number of nodes, so we always have no empty subspace for us to insert the noise for privacy preservation. And actually the same story holds for ADMM. The only difference, so we can see that the V here, V is the dual variable for ADMM, and it is actually dependent on the M and W, which is, it can be seen as the new instance matrix of a bipartite graph with the number of with twice the number of edges, and the number of nodes is m plus n. And we, based on the rank efficiency of the instance matrix, we all know that this V also have this the similar non-convergent property, just like PDMM. And so the same story also holds for ADMM. If the adversary model is to mirror the robustness of the algorithm in terms of security attack, here we consider two types of adversary model. So the first one is eavesdropping adversary. So here we have the eavesdropping adversary. It tries to listen all the communication channels, which is the edges between each pair of nodes, and so that he collected all the information he listened through the edges and to infer the private data. And another adversary model is the passive adversary model. It controls a number of nodes. So here he controls these two nodes, and these two nodes will share all the information they have to this passive adversary, so that he can increase the chance of knowing the rest of these honest nodes' private data. And one thing to mention here is that as long as, so in these two nodes, as long as one node is being corrupt, so the information transmitted along this edge will be known to this passive adversary. So we call this edge is being corrupt. And the condition for being robust to this adversary model is actually very mild for our proposed approach. So the first thing is that since we are relying on the dual variable to protect our privacy, and we can separate this dual variable into the corrupted one and the non-corrupted one. So as long as there's one neighbor is not corrupted, he is honest, so your secret is safe. And in addition to be robust to the eavesdropping adversary, as long as we make sure that the lambda 0, the initialized dual variable is not being eavesdropped, then everything conducted afterwards is actually safe to be eavesdropped. So the privacy will not be affected. So overall, we require one honest neighbor, and we require one channel encryption to encrypt the initialized step. Now let's go to the numerical result. We simulate a random graph with a number of nodes, and then we use the proposed PDMM and ADMM to show the performance. And here we can see the blue lines are the proposed approach, and the red lines are the non-private preserving approach, which means that we don't have subspace noise. So here the proposed approach, this is the subspace noise, and these two lines. And these two lines with the star and with the triangle, with the triangle is the dual variable projected into the converging subspace, and also the x, the optimization variable. So we can see that no matter we have subspace noise or not, the dual variable and the x always converge to its optimum value. So there's no trade-off between privacy and accuracy. So the same story also holds for ADMM. And in addition, we try to compare, try to see how does the different noises, since the more noise we inserted, the more privacy we have, right? So this is why we have here, we try 3 different kind of privacy level, and then it means that we try to use different noise variants to initialize this dual variable. And then we can see that in every case, this x will converge to its optimum value. So there's no trade-off between privacy and accuracy. And indeed, the convergence rate of this optimization algorithm is actually only dependent on the graph topology. It's not dependent on the initialization. So this is why there's only a slightly offset of the convergence error. So but the convergence rate is not affected. And to note, one thing to notice here in the x-axis is in the log scale. Overall, we conclude that we propose a new subspace perturbation approach to achieve privacy-preserving distributed least squares, and it's both computationally and communicationally efficient, and also there's no trade-off between privacy and accuracy. And in addition, the convergence rate is not affected. And one thing we require is that we require one honest neighbor to guarantee that our privacy is being protected. That's all. Thanks.